My name is Chloe and I'll be your maths teacher for today.
Boo!
No, don't worry, it won't be boring. We're going to look at the Fibonacci sequence.
Yay!
But what is the Fibonacci sequence?
Well, Jen, it's actually a really simple sequence. Take 1 and 1 and add them together. You then get the next number, 2. Then add 2 and 1 and you get the next number, 3. If you repeat this process, you get 5, 8, 13, 21, 34, 55 and so on. And this will go on forever. It's a very famous sequence used by mathematicians everywhere.
How on earth did he come up with that? Fibonacci looked into the mating of rabbits. He wanted to know how fast they would breed given ideal circumstances. To do this, he made 3 assumptions. Every birth gives 2 babies. 1 male and 1 female. After birth, the rabbits must wait 1 month before they can reproduce. When Fibonacci looked into the mating of rabbits, he noticed a pattern. This pattern became the Fibonacci sequence. Now let's have a closer look at this. Fibonacci started with a pair of rabbits, 1 male and 1 female. For the first month, we only have these rabbits as they're too young to mate. For the second month, they're now old enough to mate, but have to wait a month to give birth. Then, the next month, they give birth, and we have the original pair and their new babies. The original pair can now mate again, and after a month, the babies can also mate. Following this pattern, we get their original pair, their new babies, and any subsequent babies. We have shown this for 5 months, but the pattern will go on forever. So looking at the number of pairs each month, we notice that this follows the Fibonacci sequence.
But wait, that doesn't seem very realistic.
Oh no, Fibonacci's sequence is all around us. Take flower petals for example. Buttercups have 5 petals, delphiniums have 8, and chicorée have 21. Let me show you.
Let's count the petals on this flower. That's 21 petals, and we now know 21 is a Fibonacci number.
One of the consequences of Fibonacci's sequence is the golden ratio.
The golden ratio is a number symbolised by the Greek letter phi. The actual value is 1.61803399 and so on. And there is a way to get this number from the Fibonacci sequence. If you take 2 consecutive numbers, like 2 and 3, and then divide the bigger number, 3, by the smaller number, 2, you'll get a number close to the golden ratio. So, 3 divided by 2 is 1.5. 8 divided by 5 is 1.6. And if you carry on doing this, 89 divided by 55 is 1.6181. As the numbers get bigger, you'll get closer to the golden ratio.
I just don't understand.
Okay, let's try it a different way. Take a rod, say it's 100 units long, and divide this rod into 2 parts. Call the shorter part A and the longer part B. Here we have chosen A equals 38.2 and B equals 61.8. We then substitute these into the formula. B divided by A equals A plus B over B. Note that we chose A to equal 38.2 and B to equal 61.8. so that when you substitute these into the formula, it works. So, B over A equals 61.8 over 38.2, which equals 1.618, and so on. A plus B over B equals 100 over 61.8, which equals 1.618, and so on. Call those two equations 1 and 2. 1 equals 2 equals 5. This is another way to find the golden ratio.
And now, if you take A and B and make them into a rectangle, artists and architects call this a perfect rectangle. We can use the Fibonacci sequence to create a perfect rectangle. Starting with a 1 by 1 square, we can add a 1 by 1, 2 by 2, 3 by 3, and so on, to end up with a rectangle. Starting from this point, we can use the sequence to draw a spiral, a Fibonacci spiral. This can be seen in shells, tornadoes, and many other natural things. Using the size of the squares, we know the length of this side is 13 and this side is 21. If you divide 21 by 13, we get 1.615, which is close to the golden ratio. So this is a perfect rectangle. So Jen, what have you learned today?
I've learned about the Fibonacci sequence and the golden ratio. It's everywhere and you can see it in everyday life.
Did you enjoy today's lesson?
Yeah, it was really fun!